Dear friends, students and learners, I am Shashank Shrivastava from the School of Engineering and Technology, Indira Gandhi National Open University. So in the previous sessions, I was discussing with you unit number 3 of the block number 1, which was regarding ceramics, refractory and abrasive materials. So we are continuing with that, and this will be the last module for this particular unit. So first of all, in this lecture, we are going to discuss alumina silica composites. So this alumina silica composite, from the name itself, there is aluminium and there is silica, and this is a very common refractory material because of its easy availability and low cost. So it is easily available and is of low cost, so both of these things, alumina and silica, can be combined together as a composite, and they are very much used in our industries. But the percentage composition may vary from pure alumina to pure silica according to the various needs. So the most important application is in that of fire clay, and fire clay is made with alumina varying from 20 to 40%. So in a combination of alumina and silica, alumina will be around 20 to 40%. And between these limits of alumina, and depending upon the degree of firing, fire clay is further classified into 4 classes, which are the super duty, high duty, medium duty and low duty. So these duties are defined as per the softening temperatures, at what point that softening is taking place. According to these duties are defined. There is a certain factor which is given, so this factor varies according to these 4 classes. And fire clay actually is used in the form of bricks. Further moving on, there are the magnesia and the lime, that is MgO and COO. They are used for basic refractories. And basic bricks we see have greater density, high melting point temperature and good resistance to chemical attack by basic slag and oxides because of this magnesium oxide and calcium oxide. But there are refractories containing 92 to 95% magnesia, and these are used as linings in the basic oxygen steel making furnace. So this basic oxygen steel making furnace we have learned earlier in our sessions. But these refractories actually with this kind of lining are costlier. So after discussing the alumina silica based and magnesium based and ceramics and refractories, we now move on to the glasses. This is a very important category because it is very much prevalent in use everywhere. Glass is a ceramic material which is made from inorganic materials at high temperatures. So this glass consists of inorganic materials and is made at high temperatures. All commercial glasses are based on silica. So again, the main constituent here is silica only, to which we can add other oxides which progressively reduce the softening point. So there is a point called softening point, meaning the glass is either hard or soft, or at which temperature the glass is becoming soft, to what degree. So this is the basic meaning of the softening. And these oxides actually increase the thermal expansion and also affect other characteristics. Glasses have been essentially identified with requirement of transparency, strength and resistance to corrosion. So we have seen these things like in our automobiles and in our cars. We see that we need glasses, then only we can see in front and we can drive, because they are transparent, so we are able to see. So this is a very important property. And at the same time we require strength also, so that it is not broken easily by any foreign thing. And for this reason it has become indispensable, as I have stated, in automobiles and also in house window glazing. And these glasses actually have very good electrical insulating properties also, hence they can be used in electrical and electronic appliances and components as well. So now we will discuss about how this glass is produced. So glass is obtained as a fused mass after cooling to a rigid non-crystalline solid. No long order to repetitive order to molecules exist in glass. And the phenomena is like this: crystallization does not occur during solidification. So this is very important. That's why it's a unique type of substance and different from many others, because here crystallization does not occur during solidification. And hence the cooling curve, as you can see here in the graph, the cooling curve is a continuous one. The upper one is for the glass, that is given by AD. So you can see there is no breakage in the curve and it is moving down continuously towards the y-axis. But it is contrary to the cooling curve of a crystalline material, where you can see a sudden drop in a specific volume. See, this graph is between the specific volume and the temperature. So you can see the other graph, the line BC. First of all, we started at point A, and when we moved along that line, upper line, then it suddenly drops from that line AD. The specific volume suddenly drops in case of crystalline materials, and it comes to the line BC. So that's why glass is different from these kinds of solids, where there is a sudden drop in a specific volume. So this figure compares cooling of glass and crystalline solid. Specific volumes of cooling fused glass and a crystalline melt from a point as plotted as a function of temperature. At certain point represented by the temperature Tm, you can see in the curve there is temperature Tm and there is temperature Tg also. So at temperature Tm, the crystalline solid crystallizes, causing an increase in density or decrease in a specific volume. This I have told you earlier also. Crystalline solidification is continuous from B to C thereafter. On the other hand, if you see the glass curve, that is AD, it cools continuously and turns gradually into viscous liquid, and viscosity increases, and it increases to such an extent that it becomes a solid. So it is easily seen that cooling curve of glass has two distinct regions with two slopes. You can see from the dotted curves, two tangents are there, one at the point D and the other one at nearby A. So these are the two curves which have different slopes, but these two tangents are meeting together at a point called G. The temperature corresponding to the point G is shown as Tg and is called the glass transition temperature. After discussing the production of glasses, we will now see the category of silica glasses. The silica glasses include what? Fused silica, which contains small bubbles and is used for applications that require good thermal shock and corrosion resistance. So this silica glass is very good for thermal shock and corrosion resistance. We have read these things earlier: thermal shock and corrosion, etc. Fused quartz, which is transparent and used for high quality tubing, is also included under this category. And then vitreous silica, which is used for high quality optical components, like we have the glasses, spectacles also. So this falls under this category as well. Then the other types of glass and applications. So again, there is alumina silicate glass, like we discussed the alumina silicate composites earlier, similar to that somewhat. And this can have service temperature next to silica glass. So its service temperature is just below that of silica glass, and these glasses are resistant to alkalis, so they can be used for that purpose. And they are used for high performance electronic applications and other industrial applications. Then we have the borosilicate glass, which soften at slightly lower temperature than aluminosilicate glasses. So we are seeing there is a hierarchy. From this silica glass we move down to a certain lower temperature, we get alumina silicate. Then from alumina silicate we are moving down, we are getting borosilicate. So this borosilicate actually costs less, so they find wider application. Then we have the soda lime glasses. They still have lower softening temperature and higher coefficient of thermal expansion. So they will not expand that easily. So this property can be used at different places, and they are used in window glasses in buildings, and they are very cheap also. And further we have the tempered glass, which is strengthened by rapid air cooling, or it surfaces from the softening temperature. And the consequence of this will be that it will develop residual compressive stresses on the surface, and there will be tension inside the specimen. So overall strength and particularly impact strength of this glass is improved. And how we do produce it? By immersing sodium glass in potassium nitrate. It will cause sodium atoms that are smaller and to be replaced by the potassium atoms which are larger. So the residual compressive stresses on the surface will be then introduced, and the tempered glass are used in automobiles. And further we have the special purpose glasses like the photochromic, the semiconducting, ophthalmic and sealing glasses. Nowadays we are seeing so much changes even in the spectacles. Following properties of glass ceramics can be conveniently controlled as per the requirement. First of all is the property of thermal expansion, which may be matched with that of the material to which the glass is to be used. And why it has to be done? So that there is no residual stress that comes in. So both this glass and the other material that is being used, the thermal expansions will be matched. Then the properties of refractiveness, desired refractiveness has to be generated. Then the color of glass may be incorporated as per desire. Also the glass has to be made machinable in certain cases. After discussing the production of glass and its applications, we shall now discuss the ceramic production methods. So the very first method that is used for ceramic production is compaction. And here what we do, we add binder or lubricant under pressure to the ceramic. And then sintering is done. Sintering is a kind of densification of assembled particles at high temperatures, meaning we are bringing together all the particles together by compressing them with each other. And this densification occurs by diffusion processes, which you may have read in your chemistry subject. Diffusion takes place where the molecules diffuse amongst each other, and this takes place over a long time and needs high temperature. But still after this diffusion and this sintering densification process, impervious mass, getting the impervious mass is still very difficult, meaning pores will still be there. Most ceramics except the oxides may be attacked by atmospheric oxygen during sintering. So this is one difficulty that we face during the sintering process, that this ceramic is not that resistant to oxygen, so it may be attacked by oxygen. So we have to create a protective atmosphere to get a better product. Then the second process after compaction is that of vitrification. In vitrification, what is being done? Liquid phase sintering is taking place. In the earlier one, the first one, there was solid phase sintering. This is liquid phase sintering. So this is achieved by incorporating a component which melts to viscous liquid during sintering, and this viscous liquid solidifies into glassy phase in a well vitrified ceramic which is impervious structure. So this is giving us a better thing because it is giving us impervious structure. The third method is that of reaction bonding. So in reaction bonding, it is achieved by arranging for two or more components of a compacted body to react to form both a desired phase and a bond between the particles. The reacting components may all be solid, or one of them may be gaseous or liquid or introduced during the sintering process. Further, we have the processes of hot pressing. So what is hot pressing? Hot pressing, by the name itself, it requires application of pressure during sintering. Generally, hot pressing consists of applying a unidirectional pressure by the help of a plunge upon a material contained in a rigid container. But sometimes hydrostatic pressure, that is pressure from all three directions, is also applied upon the material which is contained within a membrane, and this material is simultaneously heated. So both the words have meanings. Hot pressing, compression is also done and temperature is also raised. So what are the advantages of this process? Both the above methods, meaning that one of the hydrostatic pressure and one of the unidirectional pressure, both these methods produce refractory ceramic of high density and better quality. This is also a method that requires less time than the other methods. So this method obviously is giving us better results and it requires less time, so it will be expensive than sintering, and component shapes are also restricted. Further, we have the process of pyrolysis also. Pyrolysis is the process of depositing a ceramic on a heated substrate. Like we have heard about pyrometer and all, which are related to temperature. So here also heated thing is there. The method is used to deposit, coating or produce thin walled components of graphite or silicon carbide from gases that contain carbon or silicon. So after discussing about the various methods of production of ceramics, we now move on to the refractory metals. Like ceramics can withstand high temperatures, so there are certain metals also which can withstand high temperatures. That's why they have been termed as refractory. So the elementary metals that have high melting point above 2450 degrees centigrade are defined as the refractory metals. And their alloys also show similar properties, like we are adding one metal with other, then also the properties don't go away, they remain as such, like high melting point, etc. 5 such metals from group 5b, 6b and 7b of periodic table are identified for this purpose. So from your periodic table, which you read in chemistry, from these 3 groups these metals have been identified: 5b, 6b and 7b. The refractory metals have very high room temperature ultimate tensile strength. So if we see at room temperature, the ultimate tensile strength of these refractory metals is really very good. But with increasing temperature, this strength decreases considerably, and you can take certain examples here I am giving you. That is at 1000 degrees centigrade, tungsten has UTS of 250 megapascal, molybdenum and tantalum have UTS of 125 megapascal, and UTS of Nb is still less. So we can see that at 1000 degrees centigrade, which is high temperature, all these refractory metals also have lesser tensile strength. But there is considerable improvement in strength by alloying these metals. So what are the distinctions between these refractory metals? The similarity was that they are all having very high melting point. But what's the difference actually? So we can see here that molybdenum and tungsten, like they have much higher modulus of elasticity than niobium and tantalum, and it is given in this figure also, which is being shown to you. So you can see here that MO and W have much higher tensile have higher modulus of elasticity than NB and TA. Then what NB and TA have? They have much higher solid solubility for interstitial elements. What kind of interstitial elements? Like carbon, oxygen, hydrogen, nitrogen. They have better solubility than MO and W, molybdenum and tungsten. Then niobium additionally has high superconducting transition temperature of 9.46 Kelvin. So we can see from this superconducting transition temperature that niobium can be used at very low temperatures to a range of very high temperatures. So this property of niobium is very useful. So continuing with that, molybdenum and tungsten again have significantly high creep resistance than niobium and tantalum, and this is given in this figure, which has on x-axis homologous temperature, and on y-axis it has got the stress. So you can see here that MO and W curve is somewhat higher than the NB and TA curve. That means that the creep resistance is better for them. The higher creep resistance of molybdenum and tungsten are attributed to their higher elastic moduli and low diffusivities. Like we saw earlier in this session only, that MO and W have higher elastic moduli than TA and NB. So that is again coming into play when we are seeing the creep resistance. So NB and TA, that is niobium and tantalum, they have ductile to brittle transition temperature much lower than the room temperature, but molybdenum and tungsten have the DVTTs very near to above the room temperature. So this is a problem in case of MO and W, because then they will change to brittle thing and it will be very difficult to use them. Also, one very good property of tantalum is that it has exceptionally ductile behavior even up to 4 Kelvin temperature. and we can just see that grain size, impurity content and amount of prior cold work also has considerable influence on DBTTs. So DBTT can change if we are doing some cold work or there is some impurity. So it is not a fixed thing, but still MO and W have DBTTs very near to the room temperature, as you can see from the curve also. So the temperature is on the x-axis. This curve with blue arrow is showing the niobium, and the curve with the red arrow is showing the molybdenum curve. So we can see that the ductile to brittle transition temperature for molybdenum is very near the room temperature, whereas for NB it is much better, it is much lower.